I am so glad you convinced me that the family car should be the Defender 110. It is so beautiful inside, it's so comfortable, and it just feels indestructible.
Yes, it really is. I've been waiting a long time for the new model to come out. The Defender 110, I'm telling you, it's my favorite car of all times. It's my third one. You know, I have stories of going off road. The guy managed the group. He was like, "What are you doing in this beautiful car?" I'm like, "I'm going off road." He's like, "Are you sure? Because you can use one of ours." And then they look like Mad Max cars. I'm like, "No, no, 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 we're going to do this." And he was shocked.
Wow. Well, it's great because the Defender has been reimagined for 21st century adventure, and its unparalleled off-road ability as well as its robust interior are invaluable whether you're headed towards uncharted territory or just a weekend of exploration. The Defender 110 tackles challenging surroundings with absolute confidence. The SUV conveys strength outside and in, featuring peerless technology like an intuitive driver display and an award-winning infotainment system. That's my favorite part, to keep you connected no matter where the journey takes you. Adventure is unique to everyone, and so is the Defender. Choose from the two-door Defender 90, the four-door Defender 110, or the larger Defender 130 with the ability to seat up to 8 passengers. You'll find uncompromising performance in all three. So pack up and go even further with the Defender 110. Learn more at LandRoverUSA.com/Defender.
This isn't your average business podcast, and he's not your average host. This is the James Altucher Show. Today on the James Altucher Show.
What does it mean when something that you had as a goal all of your life since childhood just crushed? How do you deal with it? How do we bounce back when we don't achieve them? Such a great conversation with Brian Keating, super smart astrophysicist, came so close to winning the Nobel Prize, but wrote a book called Losing the Nobel Prize. And he's trying to basically figure out how to see the Big Bang. It's a fascinating story, fascinating topic. Maybe soon he'll win it, and then I could say I had a Nobel Prize winner on the podcast. But even without that, let's find out how to lose one. Here's Brian Keating. So happy to have on a super genius on the podcast. Maybe he'll disagree, maybe he won't. We'll find out. He's going to explain the entire universe to us. Brian Keating, author of the book Losing the Nobel Prize, and also a professor of physics at University of California in San Diego. Brian, welcome to the show.
Yeah, James, it's only taken me about 5 years to get on. Thank you so much.
Actually, it took you 25 years of work trying to figure out how the universe works. And that's to the point where you hit the edge of our understanding of what the universe is, to the point where you almost, I'm going to say it, you maybe almost won the Nobel Prize, or you could have. What does that mean, actually?
Yeah, so the Nobel Prize, of course, is the most famous prize or award of any kind in history. I noted that recently there was a petition signed by 77 Nobel Prize winners advocating, that the president do this or that with respect to some policy on COVID. And I was thinking, why not? Why do they get to like 76? And they said, no, it's not enough. We need one more. We need 77 Nobel Prize winners. And part of it's because it has such a superlative quality to it. There's really nothing else that comes close to the Nobel Prize. So it's very much, at least it was for me, almost like an idol or something I pursued for much of my early career as a scientist. And in order to win it, I knew I had to do something that would be a spectacular breakthrough. They don't just give them away down, at the local supermarket. So you had to do something really spectacular, a discovery or an invention, according to the late, great Alfred Nobel, who left a will that became basically the most famous will in human history. And that will basically provided for prizes, monetary awards, but really it's the title that goes along with winning this award, the Nobel Prize. And one of them is given out every year in physics. And to make a discovery in physics or astronomy, as I happen to do, I knew that discovering exactly how the first moments of the universe's history unfolded would be worthy of such an accolade, in addition to the pure scientific joy of doing the research itself. I knew that would be kind of coming along concomitantly with any such detection would be a Nobel Prize.
Well, let me ask you a question, because there's lots of areas of physics, obviously. So one area is very academic, and there's like a boundary between theoretical and experimental. And you try to bridge that by saying, okay, there's this theory of how the Big Bang happened and what happened in the microseconds, nanoseconds afterwards. And you built these telescopes to look at the cosmic background radiation to maybe see something no one else has seen about what happened in those first seconds. But also there are other areas of physics. Like one can argue that, oh, any innovations in quantum computing might be worthy of a physics Nobel Prize, or studies on nuclear fusion, or maybe studies in quantum mechanics and string theory might be worthy of a Nobel Prize. It sort of seems like what's the flavor of the month or the flavor of the year that determines what's exciting and what's not to whoever judges the Nobel Prize.
Yeah, well, it's interesting. So, part of the conclusion, I always say, spoiler alert, I did not win the Nobel Prize, in case you could not tell that from the title of the book. But later, after basically my hopes went up literally in dust, I became requested to be a nominator of the Nobel Prize that, arguably myself or my teammates could have won. So it's kind of like, James, I'm flattered to be on your podcast. It's not like I've been trying to get on for 5 years, but can you introduce me to Terry Gross? I'd rather. It became like, a little bit humiliating that I was asked to nominate the winners of the prize I could have gotten, and in the instructions that I received from the Nobel Committee in Sweden was a set of criteria to use in order to determine if something was legitimately deserving of the Nobel Prize. And I'm a good academic scholar, so I went back to the original source material, like they teach us as young scientists, and I saw what Alfred Nobel really wanted is to reward discoveries or inventions that had been made the preceding year. It actually says in his handwritten will, it says that the discovery shall be, or the award shall be awarded for something discovered the preceding year. And I thought back, there's basically nothing that's ever been awarded a Nobel Prize. As you say, the flavor of the month, it's more like the flavor of the century or something like that. When by the time it takes for a discovery to be made and vetted and replicated, et cetera, it takes decades in some cases. In fact, on my podcast, I was yesterday talking to a Nobel Prize winner. He won the Nobel Prize in 2011 for the discovery that the universe is not only expanding, but its rate of expansion is accelerating. And he and I riffed on the fact that we always get these emails every day, almost, that we get an email and says, Professor Keating, I've discovered that Einstein was wrong and I can prove it. And if you help me, I will share my Nobel Prize with you. And I was laughing. They never say that about, like you said, some abstract thing about, the laws of thermodynamics or something like that. It's always cosmology or some big, huge discovery. And Adam Rees, who's the winner of the Nobel Prize, he jokingly, he's like, how do you think I got my Nobel Prize? I answered one of those letters. So you're absolutely right. There is a sort of taste that goes into deciding who wins, but some things are inarguable. I mean, the discovery that he made with his team and his collaborators, really was one for the ages, that the universe has a history that's very different from what its future is going to look like. So you're right. It's a matter of taste, and all matters of taste are subjective, right? So a lot of it comes down to other forces that tend to break the tie and who gets actually the award of society's most superlative honor.
But I guess, though, even though I called it flavor of the month, understanding how the universe began, starting with the Big Bang, what the universe looks like, what are the properties of this world that we live in. This is kind of an age-old question. As you point out in the book, it all started off with, does everything revolve around the Earth? Then does everything revolve around the sun? Then is there only one galaxy versus multiple galaxies? And so on until we kind of, reach our current understanding of the universe, which we hope is much closer to being accurate, but we don't know really what distance we have to travel still to find out what's truly accurate.
Yeah.
I mean, I sort of feel like ever since I was even though there's so many results that you talk about that happened in the past 10, 15 years, I sort of feel like ever since I was a kid, we kind of knew about the Big Bang. We kind of knew about that the static in between channels on the old, TVs was really the, cosmic background radiation that comes from the Big Bang. But just to briefly summarize and not get too much in the weeds, what is the state of understanding of the universe right now? How did we get here, and where are we?
So everything you said, is accurate. I agree with it, but it also has a sort of time translation symmetry to it, in that a person, James Altucher on the radio in 1920 or 1930 or whatever, could have been saying the exact same thing. I think we've evolved. We've got a great understanding, and really, what happens in science, and you probably noticed in the book, the scientists discover some phenomenon, and then they probe it a little bit. Then there's something they don't understand about it, and then they propose a new theory that explains the lacunae and deficiencies in the previous one, and then they find deficiencies in that, and so on and so on and so on. So I know you're a big fan of science fiction and even Isaac Asimov, and Isaac Asimov once said, if you think the Earth is a perfect sphere, you're wrong, but you're much less wrong than someone who thinks the Earth is flat. In other words, the Earth's not a perfect sphere. So what we do is we refine models of our understanding. And since antiquity, people thought the greatest minds in human history up until the 20th century, including Einstein, thought the universe was eternal, static, unchanging in a certain sense. So much so that Einstein in the 19 teens or so, about almost 100 years ago exactly, proposed this term in his equations that really wrecked them in a certain sense by adding a term that counteracted the fact that the universe should be expanding. And he basically added a term that stopped the expansion or contraction of the universe in order to do so. And this is called this vacuum energy or dark energy, which would later be discovered by my friend Adam Rees. So for thousands of years, people thought the universe was static and unchanging. Then an astronomer named Edwin Hubble in the 1920s discovered that not only were other galaxies harboring billions of stars like our own Milky Way galaxy, and not only are there billions and billions of galaxies, but almost with the exception of about 5 or 10 galaxies, every single one of them is moving away from the Earth. And that's either a sign, that we need to change our cosmic deodorant, or there's something fundamental that we didn't understand about the universe, namely that as opposed to what you might think, right? If you throw a ball up in the air, it comes down because of the attraction of the Earth's gravitational field. The matter in the universe is known to attract other matter gravitationally. And so the existence of matter really implied to people, including all the brightest luminaries of science, that the universe should be contracting or static, but it couldn't be expanding. And yet Hubble yeah.
Let me ask, and I know there's a lot to say, so
Yeah.
forgive my interruptions. Let's say the universe started with a big bang that exploded everything out. My assumption would be is that without something to slow it down, that everything would keep expanding. Like the big bang, in fact, the explosion is still continuing.
That's right. But the Big Bang model only came about because of these observations that the universe was not only not static, but that it was expanding, that things were moving apart. In other words, for millennia, Aristotle to Einstein, everybody thought the universe was either static and infinitely old, or perhaps it was cyclic, which we won't get into. But essentially, it wasn't. There was nobody who believed, even as late as Einstein in the 1920s, that the universe could be expanding. So the Big Bang, which is a pejorative term coined by an opponent of this model that the universe is expanding, a man by the name of Fred Hoyle. He coined this term Big Bang as an insult. Apparently it means something dirty in British English. I'm not going to get into it. I know it's a family show.
Believe me, it's not, but that's okay.
Okay. Over 21, are admitted only. So in this case, this astronomer and many astronomers thought that it was ridiculous, including Einstein. Einstein, when the model was first proposed, that the universe was expanding by a Belgian priest named Lemaitre. Lemaitre said, no, I think according to Einstein's own equations, the universe should be expanding, not contracting and not static. And Einstein famously said to him, I think your physics is atrocious. He was so vehemently opposed to it. But to give him his due, when Hubble showed him evidence that the universe was expanding, he quickly reversed course and later called, allegedly, this conjecture that the universe was static his biggest blunder. And, it's too bad, as I say, he could have got onto a good career, that Einstein.
Well, was that his, yeah, that's funny. Well, was that his biggest blunder, or was his opposition to quantum mechanics his biggest blunder?
Well, so I mean that's a matter that's as hotly debated as anything in physics, physicist circles. I think it wasn't really a blunder. Actually, I pointed out to Adam Rees, this Nobel laureate from 2011, who discovered the universe is not only expanding, but its rate of change of its expansion is accelerating. In other words, things are getting more and more spread out, faster and faster, like somebody's holding down a little accelerator pedal on each galaxy in the universe to move away from every other galaxy. So Adam and I were discussing that he actually, and I think that Einstein's greatest blunder was saying that his greatest blunder was this mistake, because it actually turned out to be true. He was right. The old man was right. It is true that he had this notion that quantum mechanics is not complete, and we still don't understand the so-called, what he called spooky action at a distance. But we don't fully understand it, but we know certain properties that he believed in. He used to say God does not play dice, and many other quotables. Einstein's incredibly quotable, and very brilliant. But it doesn't mean, because of the way that science doesn't really have a pope or a high priesthood, besides maybe Nobel laureates. But besides that, that he was wrong, and he could admit when he was wrong. At least in the case of this cosmic constant that he proposed to fix a bug in his equations that later turned out to be a great feature.
Hubble discovered that the galaxies are moving further apart, not just from Earth, but from each other. So it's like, correct me if I'm wrong. Every spot in the universe is essentially the center of the universe.
Every spot can claim to be the center of the universe, right? There is no center of the universe, just like there's no center to the surface of the Earth, right? There's a center to the spherical ball of the Earth, if you will, but there's no one can say that they're the center of the surface of the Earth, right?
Does that mean every part of the universe, like the cosmic background radiation, is that equally far from us in every part of it?
Yeah, so it's actually very interesting. If you take the age of the universe, which we know with great specificity to be about 13.798 billion years, and you multiply that by the speed of light, naively you would think that's like the maximum size the universe could be. But it turns out, because of the expansion of the universe actually has a diameter, meaning that if you look straight ahead of you and you look straight behind you, those two regions of the universe, wherever your line of sight terminates on this cosmic microwave background, they're actually 90 billion light years separated, not 13.8 billion light years. And that's because the universe has been expanding. So imagine the surface of the sphere again. Imagine we go to the Earth, and we don't know it, but the Earth is expanding. So every point, every city on Earth is getting farther apart from every other city. But to each observer, it looks like they're the center of the Earth's surface, in a sense, because everything's moving away from them. But in reality, there is no center, and everything, yes, is moving away from everything else, including the CMB.
Does that mean the expansion is moving faster than the speed of light?
Yeah, so the regions of the universe can expand faster than the speed of light, and this greatly troubled Alfie in Annie Hall, the young Woody Allen character. When he said he wouldn't do his homework because the universe is expanding, and his mother said, "What does that have to do with anything? Brooklyn's not expanding."
And so first off, excuse the basics, but how can the universe be like? What's actually moving faster than the speed of light?
So if you go into space, have you ever thought about this? You go into space where the astronauts are, the SpaceX guys are floating around, the NASA and Russia, and you go outside of the space station and you have a little glass box. And you take that box and you just enclose it, you open it up, and then you close it, screw on the lid. What's inside of that box? What would you say is inside of that box?
Nothing.
Nothing. Yeah, actually, there's very little inside that box. It turns out there are photons. There are some neutrinos that get you just happen to capture that are going through there, because there's a certain number per cubic centimeter throughout the entire universe of neutrinos. There may be a lot of dark matter that you can't see, so it's really not empty. That box is not empty. But now go between. Let's say there's a dark matter particle, and there's a neutrino, and there's a photon, and maybe there are some particles of the Earth's atmosphere too. And you go between those three objects or whatever. What's between those is nothing. It really is nothing. It's potential to be something, but it's actually nothing. That's what's expanding. In other words, the universe, we don't like to talk about what the universe is expanding into, because that's kind of like changing the metaphor from the surface of the ball to now the ball in your room. And so we talk about the properties of what's called space-time. So all we know is that the entire observable universe is expanding, in the sense that every point in the universe that we can observe using light or waves of gravity or neutrinos or what have you, they're all moving away from each other. And what it means to be going faster than the speed of light is just that you can actually imagine physically expanding the beach ball or the Earth's surface faster than the speed of light. And what Einstein said is impossible is for communications to occur faster than the speed of light. So you can't communicate using the speed of light and have a faster than the constant we call c. You can't actually boost that by traveling to a higher speed. But there's nothing that says that space itself can't expand, and even expand faster than the speed of light.
I see. So light being kind of this basic form of communication, that's how electricity works. That's how you could, pulse light to send off a signal to somebody.
Mm-hmm.
So all communication or information kind of stops, can't go faster than the speed of light. But other things can, as long as they're not expected to communicate with each other.
Right. Yeah. That's the information flow, if you will, is precluded from traveling faster than that speed. I mean, you can do things that go faster than the speed of light right now. So if you take like in your doorway, so you have a doorway there, and you take a piece of cardboard, just a square piece of cardboard, tilt it at an angle, and just kind of slide the piece of cardboard left and right, the intersection between where the cardboard and the door meet travels at some speed up the surface of the door. Does this make any sense to you?
I'm not
Here, I'll
sure.
show you on my screen because you can see me, I can't see you. But imagine like this is the door and this is the cardboard, and as you move this left and right, that little triangle where they meet is traveling up vertically at some speed.
Right.
Now imagine I move it like this. How fast is it moving? It's actually moving infinitely fast. So you can do things that travel faster than the speed of light. You can transmit a signal to Venus and then turn the opposite direction, transmit a signal to Jupiter, and they can't be in touch, but you transmitted them instantaneously. But they can't communicate faster than the speed of light.
I see, but their distance between each other is going faster.
Yes.
The rate of distance is going faster than the speed of light. So
That's
this is
right.
like in the. Is this related to also to the what you referred to earlier as the spooky action in quantum mechanics? So if you take the idea is if you take these two particles that are exactly alike, send them at the speed of light in opposite directions, and then you touch, you observe one, it'll change the properties of the other, and that change that. Well, that's a case where information is going faster than the speed of light, right?
Right. So that's sort of what troubled Einstein. But I can give you an example. So you just moved, to Florida from New York City, right? So imagine
Yes.
you had two pairs of socks. One was blue, two blue socks, and one pair was two red socks. And then you're packed in the dark, and you kind of did the laundry in the dark, and you put the pairs of socks together. You kind of balled them up.
As I usually do.
As you usually do. You're rushing out the door, you pack, and you get down to Florida, and you've got one red and one blue sock. What do you know instantaneously is left in the dryer at New York City?
A red and a blue sock.
Yeah, but does that convey any information? Can you use that to signal or make a stock trade? Buy Bitcoin. No, it actually doesn't contain any information because in the same way that you can say that two particles have a certain properties, what we call momentum, and you can detect them at great distances. And when you measure one, you instantly know what the other one's state is. But that doesn't mean that you can use that fact to communicate something to the original particle across the universe, separated by more than the light travel time between those two locations. So information is what is conserved. And yeah, so to answer your question, it is related, but it's more that example might highlight the problems with traveling or trying to transmit information faster than the speed of light.
So we're trust me, we're narrowing in on the topic of your book, Losing the Nobel Prize. I'm just setting the basic scientific outline of this. So one question I have is, you say the outer fringes of this expansion, the cosmic background radiation is 98 billion light years away, which is amazing considering the universe is 13.8 billion years old. But that this is sort of proof that we've been expanding at a faster rate than the speed of light. How do we know? How do we measure that it's 98 billion light years away?
Yeah, so that's a good question. So it's not 98 billion light years away from us. The maximum distance between 2 points in the universe, sort of the diameter of the universe, is about 90 billion light years, which is still much greater than the distance times the time, the age of the universe times the speed of light. So that would give you naively, let's call it 14 billion years to keep the math simple. And so actually the radius of the observable universe, about 45 billion years. So call that 3 times the actual age of the universe times the speed of light. So it's exactly like when you observe that, you can look in one region of the universe and you look in a direction, say you look completely north along your northern horizon. Your eyes are using a microwave telescope, not your eyes. And then you turn around, look south at another spot on this background radiation. Those two regions are 90 billion light years apart from one another. And yet they have almost exactly the same properties. It's as if there's a huge cosmic conspiracy that said, when James gets to be this age at this time, set your thermometer, for example, to read this exact value, 2.726 degrees above absolute zero. And the other way, and the other guy on the other side of the universe does the exact same thing. That's a pretty, hard conspiracy to arrange, one that has to be maintained for literally billions of years and across billions of light years. So to avoid that, physicists came up with this idea called inflation. And inflation basically says that actually the universe is expanded much, much faster than we thought at very, very early times. So you mentioned this in the first nanosecond. It's actually like a nano, 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 nano. It's actually a billionth of a billionth of a billionth of a billionth of a second. The hypothesis of inflation says that no, the universe underwent this expansion at 10 to the minus 36th of a second that was going faster than the speed of light, such that by the time we observe it 14 billion years later, the universe will appear to be in perfect equilibrium in all these different directions that we look. So we use these telescopes called microwave radiometers or microwave telescopes. They're kind of like satellite dishes. And we use those to measure the density, the temperature, different properties of the different regions in the universe, which without the existence of this ultra rapid inflationary expansion could never look the way that they do. And yet they do. And so it's a lacuna in the Big Bang model. It's a failing of the ordinary, regular, standard Big Bang model.
But how can we, like when we look at the sun, we see the sun how it looked 8 minutes ago, right? Because it takes 8 minutes for the sun's light to hit the earth. So when I look outside right now and I see the sun, it's not actually what the sun looks like right now.
Don't do that. I'm an astronomer. I could get people in trouble. Do not. This is not an astronomer telling people to look at the sun. This is James.
I'm wearing my thick sunglasses, but I'm looking into the past.
Yes.
But if I look at the cosmic background radiation, which is, let's say, 40 billion light years away, 40 billion years ago, there was nothing. There was no universe. It was prior to the Big Bang.
Yeah.
So how can I see something 40 billion light years away if there was nothing 40 billion years ago?
Well, so again, the age of the universe is not changing. It's not bigger than scientists think. In other words, the age of the universe is the one quantity that we're going to say we know, and we know it from many different aspects of astrophysics and other aspects of science, which is this 13.8 billion year number. Now, the question is, how can something get so far away? I mean, would that really be a question to you? Let's say I say, James, I've got this thing. It travels 10 times the speed of light, and so it's I set it off a year ago, and now it's 10 light years away from you. You'd say, no, I don't know how you did that, but assuming you could make something travel faster than the speed of light, there would be no difference. But you wouldn't say that thing is 10 years old. You would say it's 1 year old, but it's been traveling at 10 times the speed of light. Does that make sense?
I guess so. So what you're saying is in this case, the information of what happened 13.8 billion years ago happens to be 40 billion light years away. But because that whatever it is, whatever radiation it is that's out there, it's coming back to us faster than the speed of light. I mean, at least its information is coming back to us faster than the speed of light.
Not really. No. What I'm saying is that the patch of matter, the region of the universe, that volume of matter, which is basically this primordial soup of heat and protons and neutrons and croutons. No, there are no croutons back then, but there were protons and neutrons, electrons, etc. That's what we call the primordial plasma or the primordial soup. Whatever launched that particular beam of light that you're detecting now, that object is now moving away faster than the speed of light. But when it emitted it, we were closer to it than we are now by this factor of, 3 or so compared to the speed of light. So in other words, we were within what's called the horizon of that particular object or that region of space that emitted the light that you now see. So somebody shot a laser beam at us, if you like, and we were close enough where we are now, but the person holding the laser pointer, he or she is now 45 billion light years away from us.
So how do we know that there's some things that aren't even further that, we don't have the ability to see?
So remember earlier you were saying like Galileo, my hero, and Copernicus and others showed that the Earth wasn't the center of the universe. Then we saw the sun wasn't the center of the universe. Then we thought the galaxy was the center, but now it's not. And then we thought the universe may not be the only universe. Even the observable universe may not be all that exists. In other words, there may be something 91 billion light years away from us that we just in a billion years, or there could be something that's 90 billion plus 1 light year away from us. And we'll find out about that next year. Just speaking very loosely. So you're absolutely right. We don't know what lies beyond what's called the horizon. So the CMB, this light, is the oldest light in the universe. It turns out that came from a period of time when the universe is about 380,000 years old. That's when hydrogen was formed out of protons and electrons. And that light is not necessarily the farthest back we can detect. And that was the motivation to build this BICEP experiment. which I describe in the book, that was to use waves of gravity to detect the properties of the earlier universe. So you can't go farther back using light than the CMB horizon because basically we're describing what's called a plasma, as I said before. So you're right. There could be something just beyond us that we just haven't seen, and that will be coming into view as time goes on, roughly proportional to this expansion factor times the age of the universe.
Well, also, could it be the case that, you mentioned this radiation, this plasma soup started around 383,000 years after the Big Bang, because
Yes.
that's when, I guess, subatomic particles were able to merge into themselves and form these protons, electrons that created this primordial soup. Could it be the case that there's some waves that occurred right at the Big Bang that don't really exist anymore, and we haven't learned how to detect them, but they're the ones out there beyond the cosmic radiation?
Yeah, so it's exactly right. So the reason that we use this, the cosmic microwave background, is because it acts as a very, very good thermometer. You ever see these CSI shows where the paramedics show up and the first thing they do when they see an unfortunate soul who's no longer with us is they put a thermometer and they measure his temperature. Why do they do that? Do you know why they do that? Or they actually do this?
Well, to see how long they've been dead.
Yeah. So how does that work? It works by the fact that the human body is mostly water, and water cools at a certain rate. So if the room is not at 98.6 degrees Fahrenheit, the body will get to a different temperature than the room, according to a very, very accurately known equation in thermodynamics that describes how water and body material cools off or warms up. So that means you can use the temperature as a clock. Right? That would be a very weird clock, I have to say, but it's theoretically possible.
I keep a dead body around every day just for the
That's
alarm.
right. That's
so
a
I can wake up
new
on time.
timepiece from Timex, right? A Casio G-Shock gives it a different meaning. In this case, we use the temperature not of a body, but of hydrogen. We know very accurately. In my lab, I can take atomic hydrogen gas, which is just a proton and an electron, and I can ionize it by heating it up. Basically, just heat it up. Eventually, the proton and electron will break apart because there's too much energy to keep them bound together electrically, and they will kind of circulate in what's called a plasma. Turns out plasmas are completely opaque. So you can't see through a plasma using radio waves or light. And in fact, you know that because if you look at a mirror, you can't see through a mirror. And that's because the electrons in the silver or the aluminum in a mirror are very much like a plasma. So they don't allow you to see through into the next room what's behind the mirror because they basically absorb and emit exactly the photons or the light particles that would otherwise be used to peer into the other room, if you will.
But if I found waves though that were potentially thinner than light rays, I would be able, like maybe I don't know, maybe X-rays I could see beyond the mirror.
It turns out I like the way you're thinking, but you can't use light of any. So when I say light, I mean anything in what's called the electromagnetic spectrum, going from radio waves all the way up to X-rays and gamma rays. But that's not the only type of radiation. There's another type of radiation called gravitational radiation. These are waves of gravity. You can almost think about them like sound waves. So again, going to your room, you go into your bathroom, you want to know what Robin's doing on the other side of the wall. You've got this mirror, you can't see through it, but if she lights off a firecracker or something, you can hear it, right? That's using a different type of radiation, in that case, sound waves, to detect what happened farther away from you in space, which means earlier in time, right? She would have had to, clap her hands or set off a firecracker a couple of nanoseconds or milliseconds ago, and you will hear that even if you don't see it. And that's exactly what we set out to do with the BICEP experiment. We knew we couldn't see, we couldn't use higher frequency waves, as you call them, skinnier waves. We couldn't use ultraviolet light. We couldn't use X-rays or gamma rays, but we could potentially use waves of gravity to hear what the actual Big Bang sounded like in a certain sense. Again, this is a change in time of 380,000 years, which out of 14 billion years doesn't sound like that much. But a lot happened in those first trillions of seconds after the initial creation, perhaps, of the entire universe.
And so, yeah, so could, like you said, it's sort of just a blip in time beyond the cosmic radiation where the gravitational waves that were emitted in the Big Bang started coming out. It seems like it would be trivial if you had a way to measure gravitational waves, which I don't know how you do that, but that's the whole point of your quest. If you had a way to do that, isn't that just a small little notch to say, okay, now we're just going to go a tiny percentage beyond, a fraction of a percent beyond the cosmic radiation and see what was going on?
Yeah. So in big terms, is exactly what we set out to do, except we now
Where's
have
my Nobel Prize?
It's coming. Well,
I mean, that was just, we've been recording for 20 minutes and I'm already up to speed, so to speak.
I should have sent you one.
No pun intended.
I've got one. I've got one made of chocolate for you. I'll send it to you next time. So exactly, that's what we set out to do with this BICEP instrument. So BICEP was a radiation detector, but it was looking for the signals of gravity imprinted on the microwave background light. So it's kind of strange to think about. Like normally, let's say you're trying to record an explosion. Like we're think very loosely of the Big Bang as a sort of explosion. It's not technically perfectly correct. But now imagine you're going to use it. You're going to use all you have from your stock room is a piece of film, photographic film. So you could do that by in a couple different ways, right? You could use the light from the explosion to detect the flash of the explosion itself, and thereby prove that this Big Bang occurred. Or what about, if you moved even closer to the explosion, the film itself would blow up, right? It's not a great way to design an experiment. You might not get a second opportunity at it. But there's what I'm pointing out. There's more than one way to get after this particular problem. What we realized is that we couldn't capture the light using the technology that we have to use electromagnetic radiation, but we could detect the explosive sound waves, if you will, by using the only tool that we have, which is the oldest light in the universe, which is the cosmic microwave background. We used the light from the explosion as a detector, and on that light were encoded patterns, we hoped, of early waves of gravity, which could only come about if the Big Bang unfolded during this process called inflation.
Does the gravity leave a mark?
Any type of gravitation. So right now, if you're walking down, I don't know where you are, but you're walking down the street in Florida and you shake your fist back and forth, you are generating waves of gravity. All you need to generate waves of gravity is a certain amount of matter, and you have to put that matter in a certain type of accelerated motion. And so the acceleration is going back and forth. And it's exactly how you create waves of light. You take an electric charge and you shake it back and forth. And that's how electromagnetic antennas work, and that's how all sorts of things can be thought of in this way. And so you need accelerating matter. You need the more matter, the better. The more explosive the acceleration, the better. And now you can see where I'm getting. The biggest, most explosive amount of acceleration that ever took place was this period of inflation. And also, to boot, all the matter in the universe, your whole body, whatever protons are in your body that were originally formed out of quarks and heat, that was all present in the early part of the Big Bang. All the black holes in the universe, all the galaxies, the sun, the materials that went into it, all the matter in the universe was there, and it accelerated over a time period of a trillionth of a trillionth of a trillionth of a second. So it had all the ingredients to make for a source of waves of gravity that we could detect. And that's what we set out to do from the bottom of the planet.
So I know how to detect a light wave, like my eyes. Presumably, if my eyes can do it, I can make a machine that can do it.
Correct.
But how do I detect a gravitational wave?
So the detection of gravitational waves had not been accomplished as the prediction of Einstein's same theory that had within it the prediction of the Big Bang expansion of the universe that he overlooked and fought against for a little while. That same theory is called the theory of general relativity. That relativity theory predicts, in addition to the expansion of the universe, it predicts that matter traveling in a certain way will create these waves of gravity. And it also, as I said earlier, the more matter and the more it accelerates, the more production of gravitational waves.
Is there a constant like there is with the speed of light where this is the maximum speed that gravitational waves can travel?
Yeah, and guess what it is?
What's that?
The speed of light.
So now I'm confused again, because how are we gonna go beyond? Oh, because again, the expansion has moved things. We're going to get a signal from 14 billion years ago.
Yes.
What's currently 91 billion light years away.
Essentially, yes. Yeah. So we can use sound to go that farther distance into the next room, which again isn't such a big deal in a house, but going that difference. Physicists, we don't think in terms of linear time. I don't say, going to one nanosecond, from 1 nanosecond to 1 second, that's basically a second. No, I think of that as 9 orders of magnitude difference. And the physics of the universe is very different at 10 to the minus 9 seconds, or 10 to the minus 20 seconds, or 10 to the minus 36 seconds. So the physics depends on this exponent. the logarithm of the power that time is raised to. So you're absolutely right. We sought out the signal in the form of gravitational waves because photons, waves of light, left us coming up short. We can't get back in time early enough using waves of light, but we could with waves of gravity. So you ask the question, how do you detect waves of gravity? And I was making the point, it took 100 years from Einstein's prediction in 1915 till LIGO, this Laser Interferometric Gravitational Wave Observatory, led by MIT and Caltech and other institutions. They detected two massive black holes crashing together. So there's two massive, objects of matter. These are it's matter that we can't see, but they have the mass. Each one had the mass roughly of the sun times 30. So you had these two enormous black holes, 30 times the mass of the sun each. They were coalescing together, rotating at half the speed of light or so in the last milliseconds before they coalesced. It took that explosion to be powerful enough for the LIGO detectors to actually pick it up in September of 2015. And this was awarded with the Nobel Prize in 2017. And I, can talk a little bit about that.
But still, how do you know that was gravitational waves versus light waves that it was picking up?
Yeah, so that's a very good question. So what it wouldn't be light waves. It's totally insensitive to light waves, but it is very sensitive to vibrations. So what they did is they actually imagine a gravitational wave that's traveling. So it's a wave of gravity. What does it do? It actually changes your weight. So you would perceive it as traveling. Let's say it was traveling from Florida to California, where I am right now. And you're standing on a scale in Florida. If a gravitational wave came from a direction along the line from San Diego to Florida, if you think about there's a black hole that explodes or coalesces with another black hole in that direction from San Diego to Florida, and you're standing on a scale, you will feel that tremor. You will feel your weight change. It'll get alternately lighter and heavier. So you look at the scale. Why am I getting so heavy? Except you're only going up by, the atomic mass, or, it's a very tiny distortion of or increase or decrease in your mass. And what physicists realize is that you could use the change in the weight of an object or the change of position of objects to use it as a type of very sensitive scale.
So if, like, for instance, if this gravitational event happened right above me, and I'm on a scale, then I might seem lighter on the scale because it's pulling me upwards, potentially.
And just like a wave, a half cycle later, now you'd feel heavier. So and that change would happen according to what's called the frequency or the period of the gravitational wave. That depends on the properties of the black holes. But exactly, your weight would alternate periodically, and then my weight in San Diego would start going up or down, which would be convenient for me because I've been on a diet. But again, it's not going up or down that much, and so. And now I take the distance between Florida and California, and I divide that by the speed of light. And if that's not exactly equal to the speed of light, then we didn't detect a gravitational wave. You just, ate too many, pieces of sushi, and I'm just, they're totally uncorrelated. But if they're correlated with the exact time period that the speed of light separates the two locations, so these teams had to build two different identical detectors. It turned out one of them was in Louisiana and one of them was in Washington State. They both see the exact same patterns, exactly as the theory of relativity predicted 100 years ago. And they saw that in a certain direction with some degree of confidence. And for that, they won the Nobel Prize in physics, as I said, in 2017. And that's the way they built their detector. That's what's called a direct detector. So experimental physicists can do two different types of experiments. We can go and stick a thermometer in the surface of the sun, and that's very perilous, and not too many of my students want to do that. Or we can use a type of technique called radiometry, or basically like putting a thermometer on Earth and measuring it indirectly. Like you just put your thermometer outside in some background that absorbs it. And then, but those are two different methods. Of the two, it's better in a certain sense to measure the temperature directly, but indirectly does very well for something that's really far away, very dangerous, or happened long ago. And so what we were trying to do with BICEP is detect something very, very long ago that we couldn't be an eyewitness to in a proper physical sense. So we had to make an indirect detection, very different from LIGO, but fundamentally we were detecting the exact same types of objects. It's just the way that our detector was comprised of is very, very different from LIGO's direct detection.
So you're basically, you created this first telescope, BICEP, with the idea that, and telescope's a weird way to refer to it because you're not looking at something, you're detecting something, but you're basically, you're assuming, okay, beyond 383,000 light years beyond this cosmic background radiation, the Big Bang is happening, and it's going to look in some ways similar to these black holes colliding. There's going to be some event that is similar to that, that's going to emanate these gravitational waves, and you're trying to detect that. So you have this theory that you're going to be able to detect some sort of waves beyond the cosmic radiation, and and you know roughly where to look, and you built the telescope to aim there.
Yeah. So the telescope, again, it doesn't use, as you said, it doesn't use light, or you don't put your eye on it. The last time I put my eye on a telescope, for science was probably a very long time.
So you were spying on the hotel across the street from where you were staying.
My neighbor's daughter when I was a 12-year-old kid. Whatever. But in this case, it's funny because I always say I spend more time on telecons than telescopes nowadays. But in this case, we built a telescope, and the telescope could detect waves of gravity imprinted on waves of light. If you had, if this process, remember, we all agree that the Big Bang took place, but we didn't know exactly how it took place. And there was this theory called inflation that predicted if the universe accelerated faster than the speed of light for a very brief fraction of a trillionth of a second, then the universe would be suffused with these waves of gravity, which would live like light waves. So if light waves have an infinite life, they're kind of like ultimate, fountains of youth. Light never dies. So you can shoot light in one direction, it will never ever stop propagating just because it runs out of energy. Light lasts forever, and so do gravitational waves. So in particular, if this Big Bang unfurled with an inflationary component, if the universe expanded this superluminal faster than the speed of light, then the universe will be suffused with these waves of gravity even at 380,000 years after the Big Bang. So it would shake up that plasma that I talked about earlier, the protons and neutrons and electrons. It would make it vibrate or resonate in a certain way, and we could detect that resonant vibration because it would be making the protons over here lighter than the protons over there, and it would do that with a characteristic period. And we knew what we would see if inflation took place. But that's the key. We didn't know if inflation took place. You can think of inflation as kind of the match that lit the fuse that caused the Big Bang. And so we knew, as I said, before, I kind of, had always wanted to win a Nobel Prize. And the discovery of the Big Bang itself in the so-called cosmic microwave background radiation in the form of that by Penzias and Wilson, that detection resulted in them winning a Nobel Prize. And I mentioned in 2011, my friend and others, Adam Rees and others, detected that the Big Bang is actually accelerating. That expansion is accelerating. So all the more so would the actual detection of the first event in cosmic history to actually cause both of those events, if you will, or put them in motion, then that would certainly warrant a Nobel Prize. So exactly.
Right. And just to be clear, the reason we could kind of theorize that with pretty much certainty that something like a Big Bang happened is we just reverse all the equations. If everything's expanding, then at some point, if you completely reverse it, everything was at one singular point.
Yeah, if you think
it
about
has
it,
to be.
Yeah, if you think about the movie that I described before, so imagine like you're back in Manhattan, and all these you hear all these ambulances, and you hear that Doppler shift. You ever heard that Doppler, like it gets lower as it goes away? And imagine if you heard all these ambulances in every direction you listened, and they were all being it was getting lower and lower in frequency. What would you assume? That they're all moving away from you, and that motion meant that they were previously where you were. In other words, they're moving away exactly from where you are now. So you're probably, in a world of hurt because you're probably like at the scene of an accident or something. And so running the movie backwards, the implication was everything was touching. Essentially, all the matter in the universe was compressed perhaps into a singularity, a point of infinite density and temperature. And that's what, really kind of perplexed people in the early part of the 20th century in order to, really correct that and provide the impetus for what caused that explosion to start in the first place. Physicists came up with this idea called inflation.
And so, so you build BICEP, you go down to the South Pole, Antarctica, because that's the clearest view into the universe. And what do you start to observe?
So yeah, so the team that we assembled when I was at Caltech and later here in San Diego, we built this microwave telescope that's not like some huge thing that you think would fit on a rocket, or we have to blast it into space. It actually, we took it down to Antarctica, to the South Pole, because the South Pole is it's basically an ideal platform if you have to be stuck on Earth. People say, well, why don't you go to space? And I say, well, why don't you give me a couple $1 billion, because it costs that much to launch, the material and get the data, and it takes so much time to build a space mission. And the next best locations are, one is in Chile, where one of my projects is now, and that's at 17,000 feet above sea level. It turns out that the South Pole, the ice shelf, is built up over tens of thousands of years to a height of about 9,000 feet above sea level. And why is that important? Well, from your microwave oven that if you put some liquid in a ceramic cup in your microwave and turn it on for 10 minutes, you can come back and you can pick up the cup, but God help you if you touch the liquid, because it'll be super boiling, it'll be super heated. And that goes to show that the ceramic mug is very dry. It has no water inside of its molecular structure, but the water is very wet, right? So water absorbs microwaves. Why does that? What is the reason that's important? Well, we would like to be in space because there's no water. Water is going to absorb a photon that's been traveling for 14 billion years. I'd rather that not happen. Thank you very much. So we go to places that are as dry as possible. And that's why the South Pole, you remember, like, you grew up on the East Coast, I think, too. And you remember sometimes they say, oh, it's too cold to snow. You ever hear that excuse for why you couldn't get out of a school on a snow day?
I have not, actually. I always took any excuse to get out of school, so maybe I ignored that.
Yeah, I tried to use
That's why
that.
I didn't win the Nobel Prize.
That's right.
I skip school all the time.
It's biased against you, I'm afraid, my friend. So it turns out that the colder temperatures also have another benefit, in that it makes the air less humid. So that's why Florida is much more high temperature, even northern places in Florida, than California or parts of Mexico. That are drier. So humidity and temperature can go together, and you want to go somewhere very cold to get rid of as much water in the atmosphere again, so it doesn't absorb these 14 billion-year-old photons. You want that.
Why not go into space?
Again, it's very expensive. So it takes about $20,000 to launch a pound of material into space. And my experiment cost, or the first bicep experiment, weighed about 12,000 pounds. So you're talking 10 times, 100 times the amount of money, and that's if you can get a shot on a rocket. And there's many people ahead of us. And this is back in 2004 when we first started the process of deploying it to the South Pole. The South Pole is an amazing place. It really is. Very close to ideal for observing the microwave fluctuations from the Big Bang. And people have done it there for decades. And they do it both on the ice itself, which, as I said, is, it's above about a third of the water vapor in the Earth's atmosphere. In Chile, we're above about half of it. So, for 1/100th of the cost to get, 50% of the benefit, that's a pretty good, alpha ratio, as you would say.
Why can't you do it from anywhere and just take into account you calculate how much water is in the way from vapor and adjust accordingly?
Well, the famous physicist Muhammad Ali said, your hands can't hit what your eyes can't see. So in our case, we can't measure the vibrations of gravitational wave energy if the photons never reach our telescope. So it'd be like looking through the fog with a normal telescope, optical telescope, and you wouldn't be able to see anything. And you're trying to look at some scene across the city or whatever. You just can't see it. That light is being absorbed, so it never makes it to your detectors to correct for the effects of the fog or the water vapor.
Okay, so you're in the South Pole. You've got the bicep telescope working, and you turn it on, and you're starting to get you're starting to see the cosmic background radiation and the potential effects of gravitational waves on it.
Yeah, so the team that we had to be made up of a whole bunch of different characters. So there had to be people that were very good at building the instrument, designing the instrument. My role was, conceiving it and fielding aspects of it, going down to the South Pole. Then there's a whole challenge of getting the data back to North America, where we all were living and working on the analysis. Some of that was done by what they call, sneaker net, where you take a hard disk out of a computer and put it in the military plane that we all take down there, chauffeured by the Air National Guard of New York State. And we take the data, and then we have to crunch it on supercomputers, and that takes years. So it took several years just to get the data. In the meantime, we realized that the original version that I had co-conceived and built wasn't powerful enough to really make a dent. It was the first telescope of its kind, but it would need an upgrade to get to the ultimate limits that we were capable of achieving from this location. And it would need more detectors. It would need more sensitive detectors, and it would need multiple frequencies. So it had all these upgrades that we needed to make in order to make an inarguable detection.
Did that disappoint you after all this time working on it? That wasn't enough.
Yeah,
you got to start from scratch.
It sort of does, but what's funny about scientists, because you're never done as a scientist, as I said, you propose a model, you see that it's good on some things, but it has some flaws. Then you go and investigate the flaws. You find more flaws on top of the flaws on top of the flaws. It has this, guaranteed unemployment for scientists. It gives you the series of targets and refinements to make that really is very interesting, and I think that's one of the benefits. So no, I wasn't disappointed in that. It's hard because the more you get your hopes up in science, the more likely you are to make mistakes and to do things out of a desire to have nature conform to what you think it should do. And so, we tried to avoid that. I wasn't great at it. And I learned a lot from the first BICEP experiment. And then we upgraded it and made something creatively called BICEP 2. And that experiment is the one that eventually we came out with the evidence that we claimed was the first evidence for this period of cosmic inflation. And that felt very, very spectacular on one hand. On the other hand, by that time, as I describe in the book, I had kind of been taken out of the leadership role of this experimental program that I had, that I'd conceived of as a young, kind of hungry postdoc at Caltech, in the early part of the 2000s. And so that part, was much more, kind of traumatizing to me than not detecting the signal. It was, I never really expected it to work. And when it did, and then I wasn't as big a role in the discovery announcement, that's what hurt. I think that was much more devastating to me than not actually detecting it the first time around.
So it reminds me, there's like an entrepreneurial analogy, which is, I forget the guy's name, and this is part of the analogy, but there was a third guy other than Steve Jobs and Steve Wozniak who helped discover, or who started the company Apple.
That's right.
And because he kind of gave up his quote unquote leadership role, he lost his equity in everything they did. And then, now that translates to money. In your case, it translated to less academic or excellence, or less ranking in the hierarchy of academic excellence. Which,
that's right. I was kind of the Ronald Wayne is his name, right?
Yes.
And also, I make the comparison in the book between Eduardo Saverin, at Facebook, who played this huge role in the beginning, and then he was kind of forced out, and then he, kind of sued Zuckerberg and that whole thing.
So describe what happened. Like, why did you get, because people, I think when they look at entrepreneurship, they could sort of see, oh yeah, this is why someone's forced out, because other people want more money or whatever. But it's kind of surprising that the similar things, of course, ego happens everywhere, but like, what happened in this situation?
In this situation, so I had created this experiment, and a few things happened. One was, the most tragic of all, which is that my postdoctoral advisor, Andrew Lang, world famous scientist, perennial shortlist for the Nobel Prize, he took his own life in 2010. In January 2010, right after we had all returned from, constructing this secondary successor to BICEP at the South Pole called BICEP 2, which would eventually make this claim detection. And so he was kind of my, he was a father figure to me. He was I make no secrets about it. We were extremely close personally and professionally. And he really gave me the wings, the optimism to go ahead and pursue this dream of building this experiment to go back to the beginning of time. And because he wasn't there by the time we made the announcement that we had detected it years after deploying it, actually on St. Patrick's Day of 2014. We made this announcement. And the reason that I was given for being no longer included in the leadership cadre was because I had also decided to start another experiment with a friend of mine. This experiment was called Polar Bear. And the leaders of the BICEP experiment that took over the leadership after Andrew Lang's unfortunate passing, they decided that I was effectively competing with BICEP. And of course, it made me very furious because I had sired this experiment as I saw it. And,
Like, did you have arguments with people? Did this keep you up
oh
at
yeah,
night?
oh yeah,
Did you see a therapist about it? Like,
yeah, well, I did, but I'm married to her, so it was easier.
that's good.
Yeah, so in effect, when this all happened, it was brutal because I felt like I had a complicated relationship with my father, as I describe in the book, and in fact, he was a great scientist, and I always wanted to kind of best him in a sense, like kids sometimes want to do. Their father's a great athlete, and they're a baseball player, and you see him in the backyard and they're like wrestling and fighting or whatever. We were kind of like that, but when it came to science, and I wanted to outdo him, and I knew I could outdo him if I won the Nobel Prize, and that was part of the motivation that I had. I have to say, in all candor, was kind of. I don't want to say venal, but that was, it wasn't the highest angels of my nature to want to do this specifically to kind of outdo my father. But that was
But
part of it.
can I ask, and you don't quite explain in the book, but it is kind of relevant. Why do you think, Andrew, your mentor, why do you think he took his own life?
I think about that all the time. It's such a devastating thing to me and to hundreds of people. This is a guy, you look at him, he's like one of those guys, that the handsome guy from, I mean, they're all probably handsome, but from Mad Men, like I think his name is John Hamm.
Yeah.
He was like that. He was like good looking, scientist of the year in California, the whole state of California, member of the National Academy of Sciences at age like 40, had everything going, beautiful family, a wife who would later go on to win the Nobel Prize herself in chemistry, Frances Arnold. And I think he had some demons. I think I remembered him going through different periods of being extremely high, and then being extremely low, and feeling like I would do anything to get rid of the lows. I did feel this fatherly attraction, and relationship to him, and I know that he did for me. I mean, he would give me marital advice, and it was a very, very tender, loving relationship in the best possible sense in academia. And academia has this kind of structure, almost parental-like structure. No one will really know. I mean, he did apparently leave a note. I've never seen it. I don't understand why he did it. There was a recent suicide in which, at least in reports in the New York Times, a scientist, I think his name is Weitzman, who or in his mind, he had lost the Nobel Prize in economics for theories related to climate change. And this, at least his friends were saying, his colleagues said that he thought he would win the 2018 Nobel Prize. It's actually not called the Nobel Prize in economics, but whatever. It's called the Nobel Memorial Prize in Economic Sciences, but it was not to be. The prize went to two other scientists at NYU and Yale, and he was very upset about it. And they, apparently this could have played a role. I mean, again, no one ever knows why somebody goes to those lengths, but it is incredibly competitive. You said, like, well, people know in entrepreneurial situations, who founded this and who founded that. And maybe it's less so, like, like this guy Wayne that we talked about a few minutes ago from Apple, Ronald Wayne, like he didn't commit suicide. So, I mean, it's not like, being let out of certain situations drives one to mental anguish. But I think academia is really not appreciated for how stressful it is. I mean, one thing I want to have you eventually on my podcast to talk about is the fact that you can't choose yourself in academia. It's basically like you have all these hurdles. You can't choose what undergraduate school you go to, what graduate school you go to. You can't choose what postdoc, what faculty. Like, you have to go up this ladder. Then do you get tenure? Then do you get into this academy? Do you get this award? Do you get this grant proposal from the National Science Foundation? You can't choose yourself. And there's a lot of imposter syndrome and failure and rejection that takes place. And so someday I'd love to talk to you about that, and how do you actually cope with such things. But there's all unlooked mental health issues in science. It's rampant in science.
It's interesting because, in academia, there's basically one hierarchy, and you only move up and down that hierarchy. So you're a grad student, you're a postdoc, you're an assistant professor, you're a tenured professor, and then you win awards and awards and awards. And at some point, if your goal is the Nobel Prize, the highest possible award, there's the issues of winning it, and then what do you do next? But let's say you don't win it, it's this extreme cortisol-inducing rejection that just floods your system. Probably, if like for 30 years you've been powering yourself with dopamine that you think is going to lead to to the Nobel Prize, and then all of that is stripped from you, you have to be able to diversify hierarchies some way, and you might not have the capability, the muscle intact to do that.
Yeah, it's funny. I was going to send this to you. Maybe I'll send it to you later. But one of the only explicit rules. So I make the case in my book that the Nobel Prize. So it's kind of a double entendre. The title. It's like how I lost the Nobel Prize, essentially, and but also what aspects of the Nobel Prize we need to get rid of or get lost. And one of them, relates to these different restrictions on how many people can win it, how long ago can people win it if they're dead, if they died a day before, a month before, a year before the awards are given. But one of the rules, the only rule that they seem to have not changed over time, and imagine you rewrote a will and you found out that, Robin's going to change it or whatever, like you wrote this will and like nobody listened to your will. What can you possibly do to rectify that? It's one of the greatest sins in my religion, Judaism, to not kind of respect the wishes of the dead, because it's the only like mitzvah or good deed or whatever that you cannot repay. So it's purely selfless. But anyway, the Nobel rules, the only thing that they're explicitly clear about is that literally you cannot choose yourself.
So you can't nominate yourself.
You cannot nominate yourself.
It seems like also they obey the rule of you don't give it to a dead person.
Yeah, they made that up in 1974. In fact, there were two people who won it. There's been at least three people who have won it posthumously, and two of them were Swedish. And that's relevant, I think, because the award is a Swedish award. And I'm not taking away that they deserved it. I actually think that they should give out posthumous awards. And in fact, not doing so, and I've had this conversation with Nobel Prize winners, really rewrites the way that history looks back on the past of science. In other words, when this so remember I told you these waves of gravity were detected by this LIGO experiment from these two black holes?
Mm-hmm.
Yeah, so that black hole crashed into the other black hole about 1,300,000,000 years ago. In other words, it crashed together. They collided 1.3 billion light years away from us. The signals traveled at the speed of light for 1,300,000,000 years until they were detected on September 15th, 2015, September 14th, 2015. And that detection, if it had come in 10 days earlier and nothing about the history of science or anything else changed differently, one other guy would have won the Nobel Prize, and one guy who won the Nobel Prize in 2017 wouldn't have won the Nobel Prize because they have this arbitrary rule that only 3 people can win a Nobel Prize. And, I'm not saying that played a role in my particular case. I do feel like it was always very conscious. I mean, we discussed different prize-winning papers and their titles of that won the Nobel Prize when we came up with how we're going to make this announcement and who made the announcement at Harvard. And it was no accident that it was announced at Harvard. Harvard's kind of perceived as like the gold standard for everything. And, I think, by design, this was meant, and there were Nobel Prize winners in the audience when we made this announcement. But I think the Nobel Prize has this property of, like Steve Jobs used to say, reality distortion. It kind of refracts reality and how science is done. And the sad thing is that even these Nobel Prize winners admit it and they agree to it. Every single one I've talked to, I always ask them, what one thing would you change about it? And they always say, a couple different things, but they all seem to agree that it should not stay as it is. And yet none of them reject it. None of them say, I'm going to turn it down the way that I think that Sartre rejected his, and many people have rejected Nobel Prizes over the years, but no one in physics. And isn't that interesting?
So what happened then? So Bicep 2 makes this discovery. Maybe describe just in a few seconds the discovery. Like, did they see the Big Bang basically through their telescope?
Yeah, we saw these waves of gravity imprinted on the cosmic microwave background light. And so much so that, in the day that we announced it, the day after, it was printed like above the fold in the New York Times, that we had made this discovery, that we had found, the powerful force that drove the Big Bang, that put the bang in the Big Bang, so to speak.
Did you see gravitational waves that emanated from what probably was the instant, the nanosecond of the Big Bang?
That's right. So this period of inflation can only operate for a limited period of time. And what's interesting about inflation is that its properties are related to other phenomena in physics that we understand very well, things like the Higgs boson and so forth. But unlike the Higgs boson, we don't have any direct evidence for its existence because it happened 13.8 billion years ago. And there are some who say it never happened. And the reason for that is that it makes predictions that to some people sound absolutely crazy. And these aren't like crackpots. These are some of the world's most eminent scientists who say that one of the predictions, if inflation was true, so I didn't say what we did with BICEP 2 is we saw this pattern in this ancient light from the evolution of the Big Bang called the cosmic microwave background radiation. That's the heat left over from the Big Bang, from the fusion of those first elements. We saw that was imprinted with this twisting, curling pattern of microwaves called B-mode polarization or curl polarization. That's why I call the experiment BICEP, by the way. It's an acronym for the muscle that does curling, but that's another story. And that instrument detected this pattern, which matched exactly the predictions that this earlier period called inflation predicted. So we saw these waves of gravity, which was kind of like the smoke from a smoking gun. And then from that, we inferred that the gun went off. The problem is that, according to some people, there wasn't just one gun. There's an infinite number of guns. In other words, there could be unavoidably what's called the multiverse. In other words, potentially infinite number of other universes if this so-called inflationary model had been proven true. And nowadays, again, spoiler alert, it's not only did I not win the Nobel Prize, but none of us won the Nobel Prize. Not even the theorists who came up with this idea for inflation have won it, and likely they won't unless somebody makes a more convincing detection that is not undone by an interloping signal such as the one that we confronted.
So I don't understand. So how is it interloping? Like what could have happened instead of the Big Bang that would have created your signal?
So the signal can be produced in a myriad of different ways. The signal is so faint. I describe in the book, the microwave background itself is roughly about 3 degrees above absolute zero. So another way to say that is minus 451 degrees Fahrenheit. So it's incredibly, incredibly small signal. Cold temperatures that you're trying to detect. You're trying to detect the absence of heat. And then riding on top of that is a signal about a billionth or a few tenths of billions of that magnitude, so tens of nanokelvin. So there are many things that can mimic that signal. One that we considered for a very long time was that there are processes in outer space that are not related to the formation of the universe that can produce this twisting, curling pattern of microwaves that we call this B-mode polarization. One such source are particles of dust in the Milky Way galaxy that we are unavoidably forced to look through. We're riding on this galaxy, and it's not just like the Earth is just floating around in space and there's nothing around it. There's tons and tons of space junk out there, and it's not from the Earth. It's from the demise of ancient stars. Stars that lived in our galaxy in the local neighborhood where the sun is now, but lived 5 or 6 billion years ago. They, like rock stars, live fast and they died young. And when they died, they spewed out all their guts. So they spilled it out like you do on the page. They spilled out all the material that was in their inner sanctum, their core of the heart of these collapsing stars, exploding stars called supernovae. And those materials, some of them are in the form of iron and carbon and silicon, and those would form the planets, including the Earth, that we're formed up out of. And some of the other materials would go into the other planets, like methane and nitrogen and so forth. But the process of forming a planet from a dead star that explodes is by far completely inefficient. I mean, there's a lot of material left over, schmutz. That stuff that floats around in space that causes meteorites and it causes asteroids. That's all from the inefficiency of planetary formation. So the entire asteroid belt, that eventually makes the meteors and the meteorites that you have, those are really the debris, the leftover to treat us from a dead star. So on one hand, it's good because if that started and blow up and pollute the local solar neighborhood, we wouldn't be here talking about it. We literally have in our blood iron molecules, and the hemoglobin molecules in our blood comes from a distant supernova. That's why Carl Sagan at your alma mater, Cornell, used to say that we are star stuff. We have this star stuff flowing through our veins that owes itself to the demise of an ancient star. So thank God on one hand, or thank Zeus or whoever you like. But on the other hand, for cosmologists, we're also looking through a very dirty window. When we look out into the cosmos, we're seeing tons of other stuff, literally, that we don't want to see. And we knew about that. Unfortunately, we didn't have the capability to detect the cosmic signals and the dust signals with our experiment alone. So we had to rely on the kindness of strangers, and they, being, cautious scientists, were unwilling to share their data, which would have helped us convince ourselves maybe not to go forward with the announcement. Instead, we ended up convincing ourselves that we could go ahead with it, and hence led to this announcement and later essentially retracting the claim that we had made. We didn't make a blunder. we didn't leave the lens cap on the telescope or put our thumb in the frame. We made an interpretation which was later found to not be substantiated by the detection that we made.
But it still seems likely that your detection is the correct detection.
Oh, the detection is 100% bulletproof, that we detected this curling, twisting pattern of microwaves. However, and that's why I say it's not a blunder. Have been detections where they say, we detected that neutrinos go faster than the speed of light. And then they literally found, no, that's because we didn't plug in a fiber optic cable tightly enough. Like literally that happened with an experiment called Opera. No.
Oh, really? Because when I was a kid, I did think neutrinos went faster than the speed of light.
Now they go through everything, basically. They go right through us right now. Trillions of them are going through the Earth right now, unmolested. But no, it's actually not the case that we made a mistaken observation. The observation we made was exquisite. But it was we could not really rule out that dust was causing the majority of the signal that we claimed to be from cosmic inflation. And again, this was a huge, personal embarrassment for me, because along with the claimed discovery that we detected indirectly these waves of gravity, that we detected indirectly this inflationary process, came the prediction that our universe was accompanied by perhaps an infinite number of other universes. So the same day the New York Times printed this headline, a newspaper in Boston and elsewhere, they were printing things. Not only are they going to win multiple Nobel Prizes, but they also have now proved the existence of the multiverse.
So let me ask you about that. Is that because, let's say there was a singularity and it exploded in this Big Bang? Are you saying there could have been other neighboring singularities, and so the gravity you're detecting could have come from multiple, or maybe infinite number of Big Bangs that are beyond our ability to see, them because they're so far away?
Yeah, exactly. So Brian Greene in a TED Talk, he describes the inflationary process, very glowing terms, as kind of like rocket fuel. And if you remember from like the solid rocket boosters, like it's very hard to shut off a rocket. Like you can get it started, but it's very hard to turn off a solid rocket. I use the analogy in the book of like a petri dish. So if we're like a bacteria sitting inside of a culture of bacteria, once we discover that we are sitting in a petri dish, it's almost impossible for there not to be another member of our culture somewhere else in the petri dish. And in other words, you can basically infer the likelihood of of another culture, or in our case, another universe, from the existence of the petri, the goo that's in the petri dish, from you discovering that goo, that agar glue gum or whatever it's called. That substance, basically, we say in physics, especially in quantum mechanics, anything that's not forbidden is mandatory. In other words, there's some probability when you take my book and you're so sick of it, you throw it at the wall, there's some non-vanishing probability that it goes right through the wall. And of course, this happens much more readily so with electrons. We do that all the time. In fact, some of the processes we use in the lab are based on this exact property of what's called quantum tunneling. So there's a probability for that to happen. And if you can't rule out the existence of other universes, once we discovered this quantum field called inflation, we had to accept the possibility that it was not able to be shut off elsewhere in the universe. And to some, this was really good news, because they said, this proves that you don't need God to create a universe. And then other people said, no, this proves God exists, because only God could finely tune a universe in which a human being could come to exist. So on top of this was this freighted conversation that really revolved around the ancient conceptions of, where does mankind fit in the hierarchy of consciousness, other life forms, and even the existence or lack thereof of God. So you don't get that. I'm not denigrating any of my colleagues who study, magnetism and superconductivity or quantum computing. It's just that cosmology by its nature forces a person to look to the greatest heights and greatest depths of what it means to be a human being. And sometimes it raises a lot of arguments as well.
Once again, I want to recommend my good friend Jordan Harbinger's podcast, The Jordan Harbinger Show. All the time, people say, hey, other than your show, what other podcast would you recommend I listen to? And I just love listening to The Jordan Harbinger Show. He's a good interviewer. I learn while I'm listening to his podcast. Jordan, thanks for coming on the show. Recently, you had on Bill Nye. He talked about denying science, science deniers. And he also talked about radical curiosity. What's radical curiosity?
Yeah, radical curiosity. It's actually not that radical if you're a kid, right? It's looking at things with fresh eyes. And Neil deGrasse Tyson talked about this on the show as well, where a lot of times our assumptions as adults, assumptions that have actually done pretty well for us, to get us through our lives, they inhibit curiosity. And this is a good topic for you and your listeners as well, because I know, from hanging out, you and I are pretty curious, probably more so than most adults are at our age, 40 plus, whatever, however old we are now. I think a lot of it has to do with the fact that we're exposed to so many different things. Like, would you agree with that? I feel like you and I are always doing weird stuff. Therefore, we have different inputs than other people. And that's how you maintain radical curiosity. You kind of feed that curiosity in the first place instead of starving it with the typical 9 to 5, come home and watch TV kind of situation.
I totally agree. I think, basically life is almost like this laboratory.
Mm-hmm.
And rather than spend the so-called 10,000 hours to get great at something, I love the idea of learning through experiments, which Bill Nye, that's his whole message, really. It was a great podcast. It's episode 366 on The Jordan Harbinger Show. Find it where you find all your other podcasts. That's The Jordan Harbinger Show. And thanks, Jordan, for coming on.
Thanks for having me on.
So, you were trying to detect these gravitational waves. Are there, to use the way Donald Rumsfeld might describe it, are there unknown unknowns here? Like, could there be other waves that we don't, maybe those waves only existed for a really short time, during this inflationary period, and then they were just gone? What's gravity made of? There's they use the word gravitons as particles that make up gravitational waves, just like photons made up of light rays are made up of photons. Is there something else? And maybe this is related to the whole dark matter, dark energy thing, things that we just don't understand that could be beyond the Big Bang or part of the Big Bang, and maybe a deeper understanding of that is what's limiting us now.
Yeah, that's a very good question. So I'm going to have to offer you like a Lexus and a player to be named later to become a grad student again here. The notion
I'll get thrown out as I usually do. So,
so the notion that what is detectable is kind of a filter, right? So we say that we detect such and such as evidence of an underlying phenomenon. Well, that may be more of a sign of the limits of our capabilities, right? It kind of puts a filter on. If I say I only have this type of CCD camera or telescope, that means that there's only certain phenomena that I can see with that object, and so I'll be blind or ignorant of other things. But there's a whole class of other experiments. One that Einstein, who came up with the word photon, by the way. So Einstein used to use these experiments. He was a theoretical physicist, but he used to say, let's do a Gedanken experiment, a thought experiment. And these led him to some of his greatest discoveries of the constancy of the speed of light, eventually the equivalence of gravitational acceleration. So he would visualize things in his mind. And theorists are very creative. My colleagues that work on, I'm an experimental astrophysicist. My theoretical colleagues think of many other alternatives. It's basically how they spend their days because it takes so long for experiments to get their data. Even once they gotten the data, they have to be confirmed. Sometimes they're refuted. And so the process of actually the input on the kind of left side is so slow compared to the output that actually they have to come up with theories and ideas to test, even if, no one's ever going to test them. So yes, to answer your question, there are many other alternatives that could explain or could produce signals that we can see, including detections of things like dark matter, but even more exotic than that, even detecting the presence of extra dimensions. In other words, that the 4 dimensions of space and time, 3 space, 1 time, that's not all that there is. There might be as many as 10 dimensions or even more in different abstract spaces. And physicists look at that as a way to possibly explain both phenomena that we do understand, such as the existence of gravity, as you mentioned, but also phenomena that we don't understand, such as the existence of dark energy and dark matter, about which we know basically next to nothing.
And that's like 97% of the universe, right?
Yeah.
Dark matter plus dark energy. And we just know nothing about it.
That's right. Yeah.
There's not even like theories about it.
There are theories. There are no. You can't prevent a theorist from coming up with a theory. The question is, are they good theories? Are they? So, what makes a good theory? By the way, I should say this. What is the test of an idea? Many people think it's whether or not that you can detect it, but that you can prove it wrong. So this is a kind of a test that was devised by a philosopher and a logician named Karl Popper in the 1930s or so. He wanted to prove that things like psychoanalysis and astrology were really bunk and that they were total nonsense. And to do that, he said that these sciences, let's just take astrology, quote unquote sciences, aren't really representative of a true science, because no matter what you find, you can always make it consistent with the evidence. So I'll give you an example. Once I went out with my wife on a date, and we came upon a fortune teller, and she wanted to try it. I said, oh, whatever. And she said, she asked me. She said, my wife said, tell his horoscope. And so and the fortune teller, or whatever, she said to me, what's your sign? And I said, I'm a Gemini. And she went through this elaborate thing and how we're going to get married and how we're going to do this and that. And then I said, you know what? Is Gemini born in September? Because that's when I'm born. Oh no, that's a Virgo. But the same things are going to happen to you. Like, it didn't change her prediction at all. And so it's so flexible that you can't prove her wrong. You can't prove astrology wrong. Okay, she got it right that we got married. But besides that, so the point is,
maybe your wife got married to you to prove that so you couldn't falsify what the astrologer
that's
was
right.
saying.
That's the ultimate confirmation bias.
Right.
I can't imagine she did that. So in the case of Karl Popper, he wanted to show that there were things about, just like in mathematics, there's something called Gödel's incompleteness theorem. He wanted to say, what are the limits of something that is science? And it's interesting, ironically, what is used nowadays is whether or not you can prove something wrong, not if you can prove it right. And so a lot of scientists, what they'll do is they'll think about things that you could prove right, but they spend a little bit less time thinking about things that can't be proven wrong. And I think that's, it's a matter of taste, what you get into, because it's very hard to get money and funding to do something, to say that there's something you can't do, right? It's much better to say, oh, there's this exotic particle on the surface of one of Neptune's moons, and we're going to go look for it. But that being the case, despite that, I think what we do in science is really look for explanations to things that are inconsistent with what we currently know. And that's been a guidepost for science for a long time, and I think it's a healthy thing.
So now that you've kind of, this was a 20-year adventure, the bicep 2, polar bear, gravitational waves, what's, and then kind of like going right against the window of where the Nobel Prize was being handed out. What's next? Like, do you have a what's next? Or do you continue along the same path? You still hope for the Nobel Prize? Like, how do you focus your work now?
People say, you're a hypocrite, Keating, like you would have accepted the Nobel Prize if they gave it to you. And I say, well, if they offer it to me, the one way to see if I'm a hypocrite is get them to offer it to me. And if I don't turn it down, I'm a hypocrite. Actually, what I came to see is that the Nobel Prize became somewhat of an idol to me. It's literally a graven, golden, gilded object with a picture of Alfred Nobel that you must bow your head down in front of the King of Sweden on the day that Alfred Nobel died, on December 10th every year to get it. It's a very strange thing nowadays. And I realized, the people that win it, I don't have any problems with them. As I said, they can't choose themselves, so someone else chose them. But the Academy that awards it, I think that they're essentially realize that they're a monopoly, and like all good monopolies, they want to do nothing more than defend and protect their monopoly against all comers, foreign and domestic. And so my book was pretty controversial. I did receive criticism from members of the Nobel Academy, including their general secretary, who tried to take me to task on a website called The Conversation. And we went back and forth, and it came down to, really their reluctance to change rules that were never intended by Alfred Nobel long ago in the past, and also to kind of do things that perpetuate a misreading of history of science. And I'm just speaking in my case. For example, there could give the Nobel Prize to more than 3 people, but they choose to maintain that. The Nobel Peace Prize can be given out to hundreds of people, as has happened many times. And so there's nothing about the Nobel Prize in Physics that could not be modified, for example, to include teams of people. There were 50 people on my team. There were 1,000 people on the team that won it for gravitational wave discovery, the LIGO team, and yet only 3 people won it. And one of them was excluded, 4th person, because he had died, as I said, roughly if he had died, 10 days later than he did in a certain south, the waves had come in 10 days earlier, he would have won the Nobel Prize and the other guy wouldn't. So I think, for me, I'm no longer guided by that. I think, well, I do have a new project. It's called the Simons Observatory. I'm one of the co-leaders of this project. It's funded by the Simons Foundation in New York City. And this project is basically building upon the lessons that we've learned from BICEP 2. And the BICEP team is also building upon the lessons that we learned. I'm no longer really a member in good standing with the BICEP guys. It's not that they kick me out. It's just that now I'm leading and helping to lead a big experiment that is truly a competitor to what they're doing.
What's the experiment?
So my experiment is called the Simons Observatory, and their new experiment is it's called BICEP Array. It's the 4th generation in the BICEP line, and that's at the South Pole. The Simons Observatory is in Chile. And, I was thinking, an alternate title for my book was going to be a farewell to arms, basically I'm no longer in BICEP. But in this book, really I talk about where we went right with BICEP as much as where we went wrong and why and how the Nobel Prize affects and afflicts those. But for me right now, the mysteries that we can solve are still there. It's kind of like, when people finish reading Choose Yourself. Like they're kind of envious of the person who didn't read it, right? Because when you read a good book, I'm not trying to kiss up too much, but like when you have, or any great book, A Farewell to Arms, when you read that book, there's a part of you that's like, it's a little depressing, right? Because you'll never read it again for the first time. And for me, it's like we got a mulligan. Like we can do it again. We can make the discovery and hopefully make it inarguably so by taking precautions that we learned from BICEP 2 to get rid of the dust and to measure the cosmic signals. And the BICEP team is doing the exact same thing. So we're competing with one another. But the good thing about that competition is like if we both succeed, will science really progress. And I honestly can say that, people say, oh, well, you're just criticizing it. Like I said, you have sour grapes. I always say, well, it's kind of like, can you not criticize President Trump if you're not the president, or if you're not Hillary Clinton? Like, can you only criticize something if you're a member of this very exclusive set? There's more people that are on the space station in the last, 15 years or so than are living winners of the Nobel Prize in physics. It's an incredibly small group of people. And
So what about, here's an idea. So you can say, okay, I'm not going to criticize it, but let's go back to Alfred Nobel's will, and I'm going to go back for each year and basically award like an Nobel Prize to all the people who actually follow. I'm going to follow exactly the rules laid out in his will and say, this is who would have won. These are the 10 people who could have won the Nobel Prize that year because they had a discovery the year before. They were, they had this quality. You can kind of go back and reconstruct the Nobel Prize from whenever it was, 1910 to now.
Yeah, 1901 is when the first ones were awarded. Well, let me ask you a question. Imagine you do that with the Oscars, or you did that with the Olympics, or it's for subjective things, it's very difficult, right? Because it's also a matter of taste. So there are things that, like, I call them Nobel Prize bloopers. They gave it to a guy who invented a certain type of lighthouse, amplifier signal processor, back in 1912, and at that time in 1912, Einstein had already come up with the theory of relativity and had not won the Nobel Prize and would not for another almost 10 years.
Right, but that's why you can go and offer 10 possibilities and say, look, these all follow the rules. I don't know what the Nobel Prize Committee would have done that year, but these were the most famous ones, and these are the ones most cited later on. But they all follow the exact rules as opposed to what the Nobel Committee does right now.
Well, so that would be kind of like the strict interpretation. It's kind of like the Constitution. There are people that are like, the Constitution's a living document, and there are people like, no, it's a strict constructionist. So I think you'd have that, A. I think, B, you'd get no support from the Nobel Prize Committee, because what incentive do they have?
Right.
And then
Right, you'd have no support from them.
Yeah, you wouldn't. They have monopoly, as I say. Maybe a benevolent monopoly. People like it. At best, people say it's kind of like a game. I like to stay up every night. It's like Christmas night. I would like to hear when they're awarded on December 10th. But to other people, it's a little pernicious. I had somebody tell me she read the book and she wished that her dad had read the book 10 years earlier, because he basically said to her, you're never going to win a Nobel Prize, and therefore you're not going to be a good scientist, because good scientists win the Nobel Prize, so you should get out of physics. And she did. And I just think it's it has the opportunity, and the book is really written as in an attempt to use the power of the Nobel Prize to kind of agitate for change before it's too late. Because I actually think that their days are numbered. If you do a Google Ngram search and you search Pulitzer Prize and you compare it to Nobel Prize, in the beginning of the 1900s, the Pulitzer Prize was much more prestigious and appeared in many more search or book titles, et cetera. Now it's barely mentioned as it's important, it's great, but it's nowhere near the prestige of the Nobel Prize. And I think they had a sex scandal that affected alleged sexual harassment in the Nobel Prize in Literature that led to the cancellation of the prize in 2018 and deferment to 2019. And I think if they don't reform, it's kind of like Jeremiah in the books of the prophets. I'm not comparing myself, but just like he was always warning against, like, if you don't do this, this is what's going to happen. I guess that's a lot of history is like that, Cassandra's. And I do feel like for their own good, it would be good for them to kind of go back and see, as you say, what things could we have redone. And when I took this up with this guy who is the Secretary General of the Nobel Academy, who's basically one of the highest, most powerful people, he said, I disagree with you. What do you want us to do? Go back and give Rosalind Franklin's family the money that she would have won for the discovery of the double helix structure of DNA that went to Watson and Crick and one of her collaborators. And I said, no, you're making it all about the money. The money's the least important prize. Do you know that there's actually a few different prizes that are worth 10 times what you get for winning the Nobel Prize?
Oh, I don't know.
It's there's something called the Breakthrough Prize. The Breakthrough Prize, if you win it, it's funded by Mark Zuckerberg and a whole bunch of Silicon Valley guys, Yuri Milner. And if you win it, you win $3 million. And the Nobel Prize, if you split it three ways, after taxes, you take home about $150,000 in the U.S. I asked my friend Adam Reese yesterday on my podcast, what'd you do with the money? And he's like, I put some away, for college tuition. But it's nice, but it's not that much money. And so nobody does it for the money. So the Secretary General was like, you're ascribing all these venal motives to people that want to win it. Of course not. But instead, if you go to the website of a physics department or the National Science Foundation, it will tell you how many Nobel Prize winners are on their staff. That's the coin of the realm, literally. And that's the prestige that the universities and institutions get. It's not even like my friend who won it or the winners of it. They don't go around. Some of them do go around with their actual Nobel Prize, as I show in the book. But other than that, basically people are they just go back to work and continue on their work. But the institutions, they really wait. Publications get higher citations once you win a Nobel Prize. Collaborations rise and fall depending on if a Nobel Prize winner comes out of it. And it's very exclusionary. It's been very exclusionary towards female scientists throughout the years. Only 3 women have won it over the 118-year history.
But a lot of this is because we're giving that power to the Nobel Prize. We're saying this is the highest award in physics.
In your language, they're the gatekeepers. They're the ones that choose, that make the choices.
Right. So what I'm saying is, let's say you take the strict interpretation of what Alfred Nobel said, and you said, look, I'm just doing this and I'm going to do it each year, but here's what it looks like from 1901 to now, and then I'll do it each year ongoing, and I have a team with me that'll keep doing it past me.
Yeah.
And then who knows? Who knows if the story gets conferred on you that, okay, this is this is really the Nobel Prize as Alfred Nobel would have conceived of it. This is what I'm doing.
Yeah.
And I'm not doing it out of anger to the Nobel Prize. I'm just doing this based on the instructions in the will.
I actually did that. I started a website. It's now defunct. It was called Losing The Nobel Prize.org. And it was kind of like a change.org. It was like you would submit petitions for people that deserved it and people that could still win it, even according to their rather arbitrary rules, such as you have to be alive to win it. So just about 2 months ago, a colleague of mine passed away. Her name is Margaret Burbage. And she was 100 years old, and she came up with data that eventually went into the award for a Nobel Prize in 1982 for how stars produce heavy elements like the matter that I discussed in the meteorites, et cetera, iron and so forth. She came up with the data and helped with the most famous paper in history in that branch of science. And again, one of the authors of that paper did go on to win a Nobel Prize. He was a man named Willie Fowler. And so she was still alive, when I wrote my book, and I was saying, like, we got to nominate her. You got to, even by your abstract definition, she's eligible, and she never won it. Now she's dead, and she never will win it. So I did have that. I had a petition. You could upvote people. And, it just became a matter of, I only have so much time. I've got to help run this big experiment. I've got, 16 graduate students who've gotten their PhD through me and my research and their research. And, it's a matter of time. I only have so much. But yeah, I'd be willing, if people out there want to take on one of James's 10 ideas of today, I'd be willing to pay the reinstatement fee for the domain.
And it also seems like, you know, again, this is a better historical view of year by year, looking at what accomplishments were done that year. If you take the strict interpretation, right, because it's all has to be what was the biggest discovery of the year prior. So you get a much more accurate view. Like right now, when I look at the Nobel Prize winners, I don't really get a sense of the history of discovery. It's just more like, okay, here's an interesting person I should research to understand what he did. But I don't really get a sense of the timeline of discovery, which it sounds like was a little bit of the intent of the Nobel Prize. And so, again, it might be interesting just from a historical perspective as well.
Yeah, I think it is. Scholars do that. There are papers written to describe, what was the influence of the place where a discovery was made. Certain institutions have many more Nobel Prizes coming out of them. What's the influence on, specific demographic information? It's always talked about, Jews win so many Nobel Prizes, et cetera. People study those types of things. The question is, do I want to give more prestige? Like, do you want to have that as the ultimate point of comparison? And for me personally, I do feel like for me, I've moved on. I do think it's interesting to people. I do regret that it has a negative influence on people. You can't meet someone. I don't know if you ever read this article by David Brooks, but he talks about when you die. There's two different types of ways that you'll be remembered. One is by what was on your CV or your resume, the virtues of your resume, and the other one is what was your kind of ethical or moral legacy. And in terms of that, that's what's become much more interesting to me. So, and my focus now is to do the one thing that Alfred Nobel did that's impossible to quantify. So he said three things make a person eligible to win his prize. One, the discovery must be made in the preceding year. It must be made by a single person, and it must have conferred the greatest benefit to mankind. So that third thing is very subjective. What constitutes discovery? Like when we discovered nuclear fission, it led to the atomic bomb. And it won the Nobel Prize for the male discoverers of it, unfortunately, but it also agitates for good, nuclear power or green energy, whatever. I'm not going to get into that. But the point is, what constitutes a greatest benefit to mankind? By the way, they changed his will on their website, the Nobel Prizes. Now they changed it, and I'm all for kind of gender equality, obviously, but they made it for all humankind. But it's not what he said. It's very frustrating. I was imagining, my older brother's a lawyer, and like, what would he say about it? Like, as a trust and estate lawyer, going back over it, it wasn't. Sometimes we give away awards for things that are 30 years ago were discovered. Sometimes groups of 3 people, not one person, and then some of them go to things like the lobotomy, which affected terribly many mentally ill people in the 1950s and 60s. Is that a great benefit to mankind? So I looked at it and I said, what have they done to this guy's legacy? And how would I want to be treated? But I realized, again, life is short. And what I wanted to do is take the one lesson that he did give away. Again, he had no wife. He had no children. He gave away all of his riches and money to this prize. But he also included this ethical will, which in Hebrew is called a zava'ah. And I always ask my guests in the podcast, what would you put in your ethical will? I don't care about your monetary will. What wisdom, what advice, what hard-won lessons do you want to communicate in perpetuity as your legacy? And so, when you come on, hopefully I'll ask you that question. But
yeah, that's a good question.
That's the takeaway that I got from that. I also asked people what they would put on their monolith from 2001. I know you're a big sci-fi nerd like me. And so I say, if you had a billion-year time capsule you were going to put on the surface of an asteroid, what would you put inside that time capsule to last 1 billion years as a harbinger, a signature of humankind's accomplishments or your own personal accomplishments? Don't answer now. I want you to come on.
No, that's an interesting question, and I might have a different answer than one would expect. But here's another question that I've always been wondering, which is, you talked about the divide between theoretical physics and experimental physics, but it seems like there's a third divide that's not really ever discussed for maybe for obvious reasons. But you talked about Einstein's thought experiment. So he pictures a guy, I don't know, standing on the moon and the speed of light. You're a train going at the speed of light.
Well, you're going at the speed of light,
past,
and you look at yourself in a mirror. What do you see? Right. Mm-hmm.
Right. So to come up with basically, he used that thought experiment to basically come up with the most astounding, theories of physics. It's created modern physics. How much math actually do you have to know? Like we always take physics and it's like filled with math for the
Yeah.
first 20 years that you're taking physics. Do you really have to, can you be a physicist without studying physics
Well,
in the traditional way?
Yeah. So, you ever?
Well, like I can just imagine, for instance, like we could sit here talking and I could say, well, could there be multiple big bangs that had other gravitational waves that hit? So I also am allowed to do thought experiments if I want.
Yeah.
But I just don't have the math to kind of like draw it out in a
Yeah.
physics
Did you
paper.
ever read that book or hear about that book? Everything I Ever Needed to Know I Learned in Kindergarten.
Yeah.
Well, so
Robert Fulghum.
yeah, so I have another sequel to that. Everything I Needed to Know I Learned About an Advanced Quantum General Relativity, and I'm hoping you'll be my student. No, so it's exactly right. So you talk about idea sex, and I think about this as experiment sex. And experiments is a type of idea. It's a proposal. And one
Yes.
thing that I noted, again, it's a topic I'd love to chat with you more about, but is sort of the math of combinatorics or permutations. So you probably know this, but if you have a set of objects, say you have a set of fingers, you have 5 fingers, hopefully on at least one hand, unless you grew up as like one of my kids, and it's very dangerous. But if you look at your hands, how many pairs of fingers can you make? And so you can just do it with your thumb, touch your index finger, touch your middle finger, touch your ring finger. You can count up how many pairs you have, and you go, and it's 4 plus 3 plus 2 plus 1. So what's that? That's 10. So that's 10 different permutations of 5 objects. So it's not, but it doesn't scale as 2 times the number of objects. It actually scales as the number of objects squared. That's how many pairs you can have. This is called network theory. This is like how Facebook operates in a certain sense. It's called combinatorics. It's actually called choosing. From mathematics, it's called 5 choose 2. That's the symbol for permutations. In this case, the number of pairs, which is really idea sex, right, or experiment sex, it grows geometrically, grows as a square quadratically of the number of objects or ideas that you have. So you're right. In a certain sense, what you want to do is increase that n, because the output, the number of ideas or choices that you can make, grows as n squared. Now the question is, do you need to know advanced calculus? And do you need to know to make a contribution as a theoretical physicist, there's no way to do it without being extremely well versed in mathematical operations and what's called group theory and topology analysis. And even nowadays, computers are doing experiments. And yet some things you can think about these ideas. I mean, you came up with a couple different ideas that, with a little bit of polish, I can show you what paper that goes to. Now that's the idea. That's the first part. The question is, are ideas the last step? Of course not. So the hard part is going from the idea, which is an essential. So the idea is the 0 to 1. In Peter Thiel's language, but then you have to do all the hard work of scaling that out. What are the implications? What are the foregrounds? What are the backgrounds? What are the contaminating effects? How do we actually go about testing, Altucher's theory of multiple big bangs? But people do that. So it is keeping this kind of childlike, in your TEDx talk, I think you talked in San Diego and I did, and you mentioned, like kids smile, 5 times more than adults or something, right? Didn't you say something like that?
Yeah, kids smile 5 times a day. Oh no, sorry, kids smile 300 times a day, or laugh 300 times a day. But adults only laugh 5 times a day on average.
60 times more. So the question is, scientists are like children in good ways. We're very curious. We love puzzles. We love mysteries. We're also like children in another way. We're selfish. We're jealous. We're spiteful. We don't play well with others. But keeping that creativity is the first element. Like you can't get to be an adult without being a kid, right? And so I think keeping that wonder and that idea muscle going is important, but it's not the only step. And there are great examples. One of my heroes is a guy named Michael Faraday, who basically came up with all the electric motors and how we conceive of even what's called electric fields. He almost knew almost no math in the 1800 time period that he was living. His math was not his strong suit, but his creativity was. And without it, we wouldn't have, the incredible technology that we have today.
But I think back then too, though, you can have an idea and mechanically put it together to test it without the math. So now it's too difficult to do. All the things are difficult.
Yeah. Well, I think that's true, and even for experimentalists, I'm not denigrating what myself and my colleagues do, obviously, but experiments now cost, this Simons Observatory is the better part of $100 million project, and to do this experiment, to go back now, this is going to go back, trillionth of a second, perhaps, but only if inflation took place. I mean, it could be that we're doing that we come up with a null result, like that we actually don't see this. So, when people ask me, and I do get these emails, I can prove Einstein wrong. I always ask, the first thing I'm going to ask them if I do respond to their personal theory is like, have you worked through all the previous work that's been done in this field? Because otherwise they're just assuming, oh, the world has just started rotating when I was born and I don't have to look into it. It'd be like, I'm a great artist, but I've never, studied Picasso or studied Seurat or Monet. Like you don't have to be like them, but you have to understand what made them great. And great physics is like great art.
Yeah, so I agree with that. And that happens in every industry. Let's say it's math or even like you say, art or writing. You're always standing on the shoulders of the generation before you. I'm just wondering, there's the flip side, which is like you look at string theory, and sometimes I wonder, did these people just get so enraptured with the math that they got down this rabbit hole that is unfalsifiable, as you put it?
Yeah. So there's a woman, an author of a book called Lost in Math. Her name's Sabine Hassenfelder. She lives in Germany. And she was on my podcast recently, and we talked about just this, which her thesis is that the obsession that physicists have for beauty and is leading them astray. That's actually the subtitle of her book. And she explains what that is. It's a technical book. It's actually looking at things extremely, but it's a popular science book, so you could understand it for sure. But the notion that physicists have become obsessed with, say, symmetry and beauty, et cetera, it's a natural thing. You ever see this? Like they do a kind of an optical illusion or a test. They take like Brad Pitt, who's the second most handsome man in the world after the two of us, right? They take Brad Pitt,
third.
They cut his face in half, right? And then they reflect the right side over to make it into the left side, and he looks absolutely grotesque. I mean, you would not want to, I can say with confidence, I'm perfectly comfortable saying he's extremely handsome. But when you see that reflection, symmetric Brad Pitt, you would think this is grotesque. And yet we claim that we find things of great symmetry very beautiful, like the Platonic solids, the sphere, the triangle, the tetrahedron, et cetera. That those are things that reputedly have great beauty. And of course, many scientists throughout history have tried to make artistic analogs in physics, including musical analogs. I have a friend, Stefan Alexander, who wrote a book called The Jazz of Physics, in which he uses jazz to analogize the formation of structure in the universe. But you're right, there are, in theoretical physics, they're so dependent on the experimental output, which itself takes so long to get. The feedback loop, this feedback cycle, is very, very leaky, or it takes very, very long to come to fruition. And so they're guided by these sort of fundamental principles, one of which is that a theory should be beautiful. Actually, Paul Dirac won the Nobel Prize in the 30s for essentially conjecturing antimatter. He used to say things like, it's more important that your equations are beautiful than that they're correct. Which is just astounding. I say almost the opposite. Like, if they're not correct, if they don't agree with the experiment, they're useless. They're just pure math, and there's nothing wrong with math. But yes, there is sort of there's a wall at SUNY Stony Brook, where my father used to teach, and there's a wall in the Simon Center for Geometric Physics, and it has engraved in it the great equations of math and physics, and they're almost all beautiful in a sense to a physicist and to a mathematician. And I think that says something about what kind of prejudices that human beings come to. And despite the stereotypes, scientists are human beings.
Well, there's so many things to talk about. I kind of want to spend another few hours talking about all the different possible multiverses and dimensions, and I still need to understand space-time curvature. Like, we got to do another one of these. So you have to come back on the podcast and continue the conversation. But I know we've spent a lot of time. And I really appreciate the time you've spent. And
so
I've learned a lot.
Well, I want to have you on my show. I've got a list of stuff I want to ask you, and it'll be an honor to continue the conversation wherever it may be.
Excellent. And cliffhanger that leads to your show. I still have to tell you the story of what happened at TEDx San Diego when you were speaking right before me. And then I had to go on, and I almost flipped out.
You want to tell it on
So-
my podcast?
I'll tell it on yours.
Awesome.
I'll be the cliffhanger.
Awesome.
So, well, Brian Keating, I don't know what to say. You're a master physicist. You wrote also author of this great book, Losing the Nobel Prize, which was so fascinating about the history of the Nobel Prize, plus the history of the theories of the Big Bang. And it's really a good history of physics, really, and plus your experiences on the cutting edge of that. Great book to read. You should consider also being a popular science writer. We got to get you up there with Brian Greene, Stephen Hawking, and Michio Kaku, who's also been on the podcast a couple of times. Like, it's all good stuff. I'm really fascinated.
Yeah, I love those guys. The one difference between those three amazing scientists is that they're all theoreticians. And I think my book is one of the first by an experimentalist, who actually deals with getting the data. And I also wanted to make it a memoir. It's really a story of what it feels like to come up short. We always talk about the winners, but there's only one winner of a given sporting event or the promised land for a given individual, and you almost never repeat it. And so I realized that most people spend their lives in a state of coming up short, but how do you deal with that in order to learn lessons of being humble without being humiliated for not winning? And so it's really a memoir. And I'd be delighted. I also host the Into the Impossible podcast, which is at the Arthur C. Clarke Center for Human Imagination here in UC San Diego. And I'd love to have you on the Into the Impossible podcast.
Excellent. Well, I'm looking forward to it. We'll arrange that. And thank you so much once again for coming on.
Thanks, James.
These days, we're all investors, trying to be smart with our money despite our worst impulses. But at iShares, we believe that deep down inside of every investor is a better investor. One that's just waiting to be let out. Explore iShares ETFs and insights and let your best investor out. Visit iShares.com for more information.